Welcome back. This is week one, lecture four. No, it's not. It's week four, lecture one. My apologies for that. Um, just kind of shows where my state of mind is. But anyway, hopefully that won't continue throughout this lecture. Um, the scientific revolution. It's an important development, or what has been called the scientific revolution, is an important development in the emergence of modern Europe, modernity. So often, then, that has led to viewing modernity, and especially in terms of quote unquote science, as being placed in opposition to quote unquote faith, and seeing the Middle Ages as an age of faith, and the scientific revolution in early modern Europe as an age of reason, and then opposing faith and reason. That is a false dichotomy historically. I think I've tried to indicate that previously, but in this lecture, that will really be the focus. Because many of the developments of the so called scientific revolution um, would not have been possible without the scientific developments and the scientific achievements of the Middle Ages. And so we need to see if this is a quote unquote revolution. What was revolutionary about it and why? I mean, this is all part, as what we've been talking about the last couple of weeks, of this transition period between medieval culture, medieval society, medieval Christendom, and early modern Europe, looking forward then on into modern Europe. And we can say this is a change in periodization. And in every change of periodization, we have a transition phase. In some ways, right now, in our world today, we are in this transition phase from a modern view of things, a modern period, to something that comes afterwards. And we don't really have a good term for it. That's what I think I've mentioned before. I think if I haven't, I should have. But then I'm mentioning it now. Postmodernity. And we'll be hearing more about postmodernity as we go through this course later on, too, what that term refers to and the various ways that it can be used. But the point there is that we are all of a sudden, not all of a sudden, but we gradually have found ourselves in a society and culture that doesn't really fit what we had thought was the definition of being modern. Now, modern on one level can just mean like us, and it's a term that had been used all along. In the Middle Ages, they had the modernity, those people who were modern, which were just kind of the avant-garde, so to speak. That's a French term, the avant-garde, the front guard, the foreguard. Moving history forward, moving culture and discovery forward, and on we go, and on we go. And the historians interpret these developments based on the sources, and we evaluate. And we look at what had come before, and we distinguish that from what we're seeing at whatever period we're focusing on. Here, early modern Europe, scientific revolution. And we see a gap, a chasm, a caesura between two periods. Now, another way of looking at this transition or these two periods and what that all means is actually drawn from the work of the philosopher of science and the historian of science, Thomas Kuhn. And Kuhn put forward a theory of scientific revolutions. He also has a book on the Copernican revolution, which we'll be talking about a little bit more later on in this lecture. And what he argued is there is something called a paradigm. Now, a paradigm is a worldview of how everything works. And when everything kind of makes sense according to a given view of understanding it, then there are not all that many reasons to question the paradigm itself. You can also think of a paradigm as an overarching governing ideology, not just politically, but intellectually as such. What are the things that we assume are the case? What are the things that we assume about the way the world works? And within a given paradigm, when that has been established, change takes a long time. It doesn't change overnight. We've talked about revolutionary change and whether this period of revolution, whether the scientific revolution was a revolution. We talk about whether the Reformation was a revolution. Somehow, what was going on in this period between, let's say, 1500 and 1800? It's the end of one world or one paradigm and the emerging and then settling in of another paradigm or overarching ideology. And that doesn't mean that everybody there was had the same view of things. And I don't know if I'm going to mention this later on today. I think I probably will when we talk about Copernicus. But I think I already mentioned it in terms of talking about Columbus and the Age of Discovery and things. Every educated person in the Middle Ages, knew the world was round. They knew it was round. The circumference had been measured by the Greeks already. That is not to say that then there weren't people, medieval peasants and things, who did think the earth was flat, because, frankly, when it comes down to it, that's our experience, is it not? We know the earth is spherical. But when we go out and take a walk, or when we get in our car, we're not thinking about, I get to go around the globe. We might do that when we are in a plane, and if we go up high enough, we can see the curvature of the earth and those kinds of things. But our daily life, our experience, is that the earth is flat. So it makes sense to me, in any case, that there were people in the Middle Ages who just thought the earth was flat. They didn't think anything more about it. They went about their daily lives, and that was that. But every educated person knew it was spherical and knew that it was at the center of the universe, period. And knew that the sun orbited the earth. We still talk about that. The sun will rise this morning at whatever it is, and it will set this evening at whatever it is. In that sense, we're still in a pre-Copernican experiential world. Now, the scientific revolution changed the paradigm of the natural understanding of the cosmos. It was slow in coming. And to understand what that change really was, we need to start with medieval science and the medieval cosmological view of the natural world. But it's in this period of the 17th on into the 18th century that, quote unquote, science is born as a discipline, or as a series of disciplines. Scientia, which is the Latin that is translated directly as science. Scientia in Latin just means knowledge. And in the Middle Ages, there were no scientists. There were various sciences. And there were philosophers. Philosophers as individuals pursuing the discovery of truth, the love of truth. And there were people who did natural philosophy, seeing the truth in the natural world. And what was it? But in the course of the 17th on into the 18th century, by the end of the 18th century, science as a discipline, distinct from philosophy, distinct from theology, had emerged based on mathematics. Now, we'll see some of these developments as we go through this, but what I want you to realize is that, as so often portrayed, it's not that the Middle Ages were an age of faith, and all of a sudden then the age of reason with science, in opposition to what had come before, came about. But we'll see that as we go through it, I hope. Now, that being said, we start with medieval science, which of course is going all the way back to the Greeks and the Romans, because the Greeks, the medieval scientific understanding was basically based on Greek science, and Greek science was then transmitted to the Latin West via Roman science and understanding, and it was then just continued for the most part, but I'll talk more about that as well shortly, in the Western tradition. Now, early on in the Middle Ages, the level of understanding of classical knowledge, of classical sources and culture, had very much, I'm not going to say disintegrated, but declined. Boethius, I don't have this on the slides because I actually wasn't planning on talking about this. I was just going to jump right into the middle of medieval science. Um, but Boethius was a 6th century figure, late 5th, early 6th century figure. He was a politician, a statesman, a philosopher, and he realized that the knowledge of Greek in the West was disappearing. And so he said, what I'm going to do, I'm going to translate into Latin all of Plato and Aristotle, because they wrote in Greek, and their works were circulated in Greek. And he started out to do that. He didn't get very far. He translated some of Aristotle's early logical works, the Categories and the Prior Analytics, I believe, but didn't get very far. Plato was known simply in the Latin translation of the Timaeus, which actually I don't think it was Boethius' translation. It may have been, but I don't think so, because other people had translated some of Aristotle too. And the rest of Plato was not known. And Aristotle, the rest of Aristotle was not known until, as I'll be talking about later on, till the later 12th century. So there was a decrease in scientific knowledge or understanding, or let's say natural philosophy, a decrease in the understanding of Greek natural philosophy. And yet there was a need to understand how the heavens moved. And yes, there are manuscripts showing that the angels moving the heavenly spheres. I'll be talking about the heavenly spheres in a moment. But by and large, it was seen as natural. I'll talk about the de-animation of the heavens as well. But the point was, we need to be able to date, and here we go, very practical theological issue, religious issue. When's Easter? That's going to be important. Dating Easter. Because Easter is not a fixed holiday. Christmas is a fixed holiday. December 25th. Oh, yes, great. Every year it's December 25th. Easter moves around. Depending on, I forget what the formulation is. I don't even know if I ever, it was like the 13th month after Nisan or 13th moon after Nisan or something. But in other words, you had to observe astronomy. You observe the heavens to determine when was Easter. Today, I could give you an assignment. Tell me when Easter is in the year 2125. And you could go and Google it. When is Easter in the year 2125? And boom, you get an immediate answer. Because those tables have all been done and calculated. Now, pretend you didn't have any of that. Pretend you didn't have a computer in Google. Pretend you didn't have a telescope. Pretend all you had was your eyes and a quill and a piece of parchment to write on. And like when Easter had been celebrated, but when will it be celebrated next? You know the formula, but can you figure it out astronomically? And when might it become in 10 years from now? So the whole point of this is that mostly monks started to observe the cosmos to try to discern when Easter would be. And this is, you say, isn't that a ridiculous reason? It's like, not the time, not at all. This is an important reason. And this is kind of the early forms of astronomy, to observe the heavens and to then figure out the date of Easter for the coming year and the year after that and the year after that. And they would make Easter tables. And the Venerable Bede, one of the formidable scholars of the 8th century, 7th, 8th century, wrote a work called De Ratione Temporum, on the calculation of times. Determining the calendar was important. The calendar, they knew, was kind of off. They were using the calendar, the Roman calendar from Julius Caesar, who established it, and so, but it kept not being quite right. And how do we know about Easter? So it's that approach to observing, describing, mapping the universe and what is known about it and how that affects Earth. Now, that's kind of the background in terms of some of the discussions that were going on about the natural world. Everybody agreed and knew that God had created it all, but that's like, okay, fine. So what? How can we understand it based on how it actually works? Now, I have up here on the slide the Age of Reason under medieval science and then the Ptolemaic universe. And in terms of the Age of Reason, um, there's a lot of reasons to refer to the Middle Ages as an age of reason, because reason and the reasoning defined the age, at least from the 12th century on, and certainly before that as well to a degree. There was not an opposition of faith and reason. St. Anselm, in the late 11th, early 12th century, wrote his famous ontological proof of God's existence. And he said, I believe, but I want to understand. So can I prove God's existence simply based on reason? He says, yes, I can. Because God, by definition, is that greater than which nothing can be thought. And then he has an elaborate deductive logical approach to then proving why it's necessary that God exists. There were arguments back and forth, but that's using pure reason, that approach. And they did the same for what they observed and saw. I mean, Anselm's was a mental construct. It was a logical mental construct. It wasn't based on observation. It was simply sitting in his room saying, okay, can I prove God's existence? Because I can't go out and look because God's not there. Maybe what God created is there, but God is not there. So how do we know? Another aspect of the use of reason was in theological debate, especially as Europe came in contact increasingly not only with Jewish scholars, but also then with Islamic scholars. They had to somehow refute their positions to argue, as a logical argument, why Christianity was correct and Judaism or Islam was not. This whole debate culture that I think I talked a little bit about in the early lectures was central to this whole approach of reason and rationality and how it works together. That would stay the same, as we will see shortly. And what was reasonable in terms of how the universe worked was the model that Ptolemy came up with, the Greek natural philosopher. And there's also an Aristotelian version, but they didn't really know that much about the Aristotelian version until later. But the Ptolemaic version, they kind of know, with the Earth at the center, because that's what we observe. And based on observation, just think about it. I could give you the date, the task of telling me when Easter in 2025 is going to be, or 2125, when is that going to be? And you can look it up pretty quickly. But if I said, okay, you cannot use the internet, you cannot use the library, you cannot use anything other than your own eyes and your reason, could you do it? One, I think it'll be very difficult because we can't see very much because of the light pollution. You have to go somewhere where you can actually observe. You can't use a telescope. You can't use anything like that. You just have to look at the stars and then tell me when Easter is in 2125. That's what the medieval scholars were doing. Now, the Ptolemaic universe accorded with what was observed. And if you look up here on the next slide, I'm still with the Ptolemaic universe, so I'll come back to this slide after I show a couple of things. We have here the Ptolemaic model of the universe. And here, this is a modern depiction of it. With the Earth at the center, then the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and then what was called the fixed stars. This is a system of concentric spheres, so that the Moon orbited the Earth on a sphere. It's almost like, if you think about it, those things where you open things up and keep opening things up. There's like the Earth is at the center, and then there's a sphere that goes around the Earth. The whole thing is like a globe or ball, and that is then the moon. And then there's Mercury on another sphere that's rotating, and then Venus, and then the sun, and on it goes, and then the fixed stars, or the outermost sphere. And the question was also asked, what would happen if you were standing on that outermost sphere and stuck out your arm? What would you stick it into? And the answer was you couldn't, because the universe is closed. It's rather small and it's closed. They didn't theorize too much what was beyond the fixed stars except heaven. And you couldn't stick your arm into heaven. So the concept was that this universe with these concentric spheres moved by natural motion, which I'll be getting to, and it moved by perfect circular motion. That motion caused music, because we know that motion causes music. You pluck a string, it moves, and it makes a sound. That's called the harmony of the spheres, the celestial music. And if we could just discern and listen carefully enough, we could hear the music that the spheres make as they're orbiting. Just think about it for a minute. They knew the planets, and they were called planets. They knew the sun, they knew the moon, they knew everything up through Saturn, and they knew the fixed stars, which is like the zodiac. There's a problem, because if you start charting and tracing the fixed stars, it's very clear. They just go in a circular motion. The planets, though, planetae, that's the Latin, planetae, the planets, were seen as erratic stars or irregular stars because they moved circularly and they orbited, but they also then did weird things. They started was called retrograde motion. So they would move along, and then they'd kind of loop back, and then they'd move along, and then they would loop back, and then they'd move along. How do they account for that retrograde motion? So this goes to the next slide there, which is called a theory of epicycles. This is an epicycle reproduces retrograde motion within the constraint of a circular motion. What we see here is that the circle A, bisected through the diameter AD, is the sphere. The planet is P, and the planet actually does not orbit on the sphere, which just goes around and around and around, but orbits a point on the sphere. So the planet orbits F. So the planet is orbiting F, going around, and as the sphere is going around, and that leads to the observed motion, which is there at the bottom. You can kind of see how it works itself out. That was charted based on observations. That's why they were called the planets were called the erratic stars. Now, we know they're not stars, but they were called the erratic stars. And it worked pretty well. Medieval natural philosophers could predict eclipses. They could, lunar eclipses and solar eclipses, and account for them. They became very sophisticated in terms of calendrical adjustments that were needed every so often. And they, for the most part, it worked. The Ptolemaic system worked for their everyday life, all based on observation and accounting for what was observed. Now, Aristotle came along and had not a theory of epicycles, but a theory of not just those 9 spheres, but of 55 concentric spheres, each one kind of going different ways to work it all out. Now, first of all, my spatial imagination, my spatial grasp is not very good. I think abstractly, I don't think spatially. So I can't really explain how that all worked out in terms of the epicycles and everything else, but supposedly it did. Much less can I explain how Aristotle's model of 55 concentric spheres worked. I can't. But somehow it all kind of worked out, more or less, and certainly by far more than less. So there were some issues that they were aware of, but like it was approximate. It got pretty close to what they could observe and chart as they would go through. So that is a development that was there. And as this system is developing, and as scholars are looking at it more and more, and in some ways, as some of the problems and glitches begin to bother people, we have a development in the 12th century. So the 1100s, the scholars have referred to as the 12th century Renaissance. This was a broad cultural movement. It's not simply based on natural philosophy, but that was part of it too. And what we see here is a real emphasis on natural causation, not divine causation, natural causation. What makes things move? How do they move? How do we understand it? We have a book. Here's a book. And what happens if I let go of it? They could explain that. Something called gravitas. Gravitas was seriousness, weight. And they'll talk about in a second. They analyzed, scholars in the 12th century started analyzing all that was into 4 elements. Now, if we look at then the next slide, we see the 4 elements. And there on the left side, underneath element, we have earth, water, air, and fire. You may have heard ancient Greek philosophers, pre-Socratic philosophers, as they were called before Socrates, and Anaximander said, everything is water, or everything is fire. And you think, well, that's ridiculous. They don't mean everything is a flame. They didn't mean everything is liquid like what goes on in the water. What they meant was there's a single element from which all the others derived. And an element was a building block of all physical reality. So these 4 elements, earth, air, water, and fire, were as abstract as our elements. Or elements of what? There's 118, 20, however many on the periodic table today. These elemental substances, elemental things, hydrogen, oxygen. On we go. I had to memorize the periodic table for high school chemistry, which was a good thing, I think. My sons didn't have to when they took chemistry. They just said you can always just look it up, and I thought that was an abomination. It actually helped, anyway. But I forget even how many elements there were when I was in high school taking chemistry and having to memorize 108 or 110 or something like that. I think now it's up to something, I don't know. But the point is, we still have these fundamental building blocks of elements that comprise everything. The medieval natural philosophers did too. They called it earth, air, fire, and water, or water and fire. And each of these elements, as you can see there on the slide, had their own distinct natural quality and their own distinct natural motion. And Earth's quality was cold and dry. Natural motion then was down. And how was down defined? Down was defined as toward the center. They knew the world was round. So on the other side of the world, down would be like up from where we are, etc. Never mind. But it's up was away from the center, and down was toward the center. Water was cold and wet, and natural motion down. Air was hot and wet, natural motion moving up. And fire was hot and dry, natural motion moving up. And this got to be a very elaborate scheme. And one 12th century scholar, we know only by the name of Marius, wrote an elaborate treatise on the elements, De Elementis. And was edited and translated by one of my undergraduate professors, Richard Dales. And Dales argued that basically, Marius had developed analytical chemistry. Because what he argues is with all these different combinations and how it's all put together, you can analyze everything that is based on these 4 elements. That's quite impressive. Quite impressive indeed. And then they did thought experiments, and maybe they even carried out some of these thought experiments. How do we know that fire moves up? Well, very simple. Take a candle. Now, the candle itself is primarily made out of earth. I mean, all things are a composite of all four elements, but in various proportions. But a candle, the predominant element is earth. How do we know? Well, if you drop the candle, boom, it falls to the ground. Natural motion down with its gravitas that weighs it down and brings it down, natural motion towards the center. But when you light the candle, the flame is always going up. This is what happens if you're holding the candle, a lighted candle with the flame. Yeah, there we go. You turn it upside down, the flame still goes up. You'll burn yourself. Obviously, the flame is predominantly fire, and the fire is still going up. Thought experiments like that ruled the day to prove how this system all worked. And again, I said, for everyday life, it worked very well. Why do things fall to the ground? Because of their natural motion. And I have to exert violent motion on that book that I dropped to pick it up. I have to bend down, reach over, and pick it up contrary to its natural motion. There was natural motion and violent motion. And violent motion was motion contrary to natural motion. This would later be referred to as force. You have to exert a force on something at rest to bring it to a different state and to move it. But we'll be getting there when we get there. Now, I have also up here a great quotation from Adelard of Bath. Now, Adelard was a Benedictine monk. And somewhere between 1107 and 1133, he wrote this work called Natural Questions. Now, Natural Questions was actually the title of a work by the Roman author Seneca, in which he was kind of summarizing Greek natural philosophy. And Adelard does that, but he does it as a dialogue with his nephew. So he's talking with his nephew about the natural world and things. He's describing and teaching the nephew about the elements and how everything else works. And his nephew is being argumentative. He says, Uncle Adelard, I don't believe you at all that everything is a composite and receives nourishment from everything. Because here's my thought experiment. If you have a plant, if a plant is composite, okay, but what happens if you pluck the plant up out of the ground? If it's a composite, as you say, it should still live because it still gets nourishment from air and water. But if you do that, it dies. Therefore, what you're saying is hooey, and we have to attribute everything to God. Because it's only God that makes things live. It's not this physical, natural causes that you're talking about with the elements, and the plant being yanked out of the ground proves it. And then I quote for you, I give you the quotation in translation of Adelard's response. He says, I take nothing away from God, for whatever exists is from him and because of him. But the natural order does not exist confusedly and without rational arrangement. And human reason should be listened to concerning those things it treats of. But when it completely fails, then the matter should be referred to God. Therefore, since we have not yet completely lost the use of our minds, let us return to reason. 12th century Benedictine monk. And he goes on to explain why it is that when you pull a plant out of the soil, it's going to die. And even though it's a composite, it's not going to receive enough nourishment from the water and air to live. Now, I'm going too much into all these things. I could talk a lot more about medieval science, and I actually designed a course on medieval science that has never been taught, actually, for reasons I'm not quite too sure why, but that's another issue. So I haven't reined myself in sufficiently here. But I think it's also important to understand what was going on in terms of the natural philosophy in the Middle Ages. Because this whole approach to nature, to reason, natural causation, which led to what also Dales is referred to as the deanimation of the heavens, when it's by no means simply referring to angels to move the spheres, but there's natural causes for everything. And he says, it's this attitude, this search for understanding the natural causes, which led to the recovery of Aristotle. And this was a major transformation in the understanding of medieval intellectual development, because the earlier view, prior to the 70s and 80s, when Dale's publishing his articles and books about this, the earlier view was that what the developments in natural philosophy in the Middle Ages all stemmed from Aristotle. So we have the recovery of Aristotle, and then reading Aristotle, also along with the Arab commentators, and I'll talk about that in a second, that then led to this new natural understanding, the focus on natural causation, some of the developments of the 14th century, which were pretty impressive, and on we go. And Dale says, no, the attitude came prior to the recovery of Aristotle. Because just think about it. What do you have to do to all of a sudden recover Aristotle when it's not available in Latin translation? You have to learn Greek or Arabic to translate it. That's quite difficult. Adelard, actually, Abath, was part of the process. He went to learn Arabic so he could translate Aristotle's treatises that had been translated into Arabic, from Greek to Arabic, and then Arabic into Latin. And there are other scholars who learned Greek and could translate them directly into Greek, but I'll talk about that in a second. But this understanding of natural causation, that even though there's God, we don't take anything away from God, but we don't appeal to God unless we can't figure it out, unless we can't find the natural causes of things based on reason. And only when we kind of hit a wall and can't come up with the solution, then we say, okay, the only other possibility is we have must be divine causation. I mean, everything was divine causation originally or ultimately, but something called secondary causes. It was all natural causation. Now, this is the approach, the attitude, the model of the educated people. Also, then at the universities, became very much established, except Aristotle had a problem at first, early on in the universities. But by the mid-13th century, Aristotle was the required reading for everybody in his natural philosophy as well as his logic. The logic had always been there, but at first, in the early 13th century, when the new Aristotle was recovered, it was condemned and not allowed to be lectured on, but that didn't keep people from doing it. Controversy, and by the 1255, Aristotle was required everywhere for the arts and for theology, and on we go from there, but that's a separate aspect. Now, with the recovery of Aristotle, if we look at it as this new attitude, new focus on natural causation, leading to the desire to put the effort in to recover Aristotle. Aristotle had not been lost in the East. So what I mean by here, Constantinople and the Islamic world, the Greek world and the Islamic world. The Latin world, as I've already said, had lost most of Aristotle. So this attempt to recover Aristotle was an attempt to translate Aristotle into Latin. You could do it both from Greek, directly from Greek into Latin, or you could translate it from Arabic into Latin. Both approaches went. In Cordoba in Spain was one of the real centers, because if you remember, I think I mentioned this, the Crusades, Islamic forces had come all the way into Spain until they were stopped by Charles Martel in the Battle of Poitiers, or the Battle of Tours in 732. But Islamic culture remained there in Spain, or what today is called Spain. So there were centers where there were Arabic scholars. Arabic scholars all the way back in the 9th, 10th, 11th century have been reading Aristotle, studying Aristotle, and commentating on Aristotle. And both in terms of Greek manuscripts and in terms of the Arabic manuscripts that were being translated, often they were transmitted along with these great Arabic scholars, Avicenna, Avesbron, Averroes. Three of them were the primary ones. And Averroes was just known as the commentator. Aristotle became known as the philosopher, and the commentator was Averroes. Um, and so you get this great Islamic commentary on Aristotle, along with Aristotle. And that too was somewhat controversial, became somewhat controversial, but by and large was not a major problem. That then contributed to the further desire to continue translating Aristotle, also right from the Greek. So these two modes of transition, and that then just accelerated the interest in the natural world. Because Aristotle was one of the things he focused on was the natural world, physics, astronomy, psychology. If we can understand all of these different disciplines, now even more so with Aristotle's help and the help of their Arabic commentators to explain what Aristotle was meaning and getting at, we can then move forward. And it was on that basis that then we see what can be referred to, or Dales referred to as the scientific achievement of the Middle Ages, which was quite impressive. The ability to map the cosmos, the ability to, in the 14th century, almost develop calculus in Oxford, at the 14th century Oxford, known as the Oxford calculators, to understand lunar and solar eclipses, to be able to chart the tides, and to realize that the tides of the ocean are directly related to the moon and the effects of the moon on the earth. And on we go. Also, some of the technological advances, lenses, glasses, had been developed. The mechanical clock had been developed. So there was a lot of technological developments based on natural causation, the physical world, a lot of theoretical understandings of the natural world that all made sense. And it all worked. It all fit. And so when another scholar, another priest, a Polish priest, questioned what had always been assumed, there was some controversy. Some scholars thought, you know what, he has a good idea. Other scholars were like, no, that's wrong. Can't, because that would overturn everything. The person I'm talking about now is Nicholas Copernicus. So if we go to our next slide, Nicholas Copernicus, 1473 to 1543. He was born in 1473 and he died in 1543. He was, as I said, a priest. He studied in Bologna. He was at the University of Krakow for quite a while. He was Polish himself. And he noticed that there was a problem, as did everybody else. Namely, the calendar was a bit out of date. The calendar was a bit out of whack. And so, even though this Ptolemaic system worked for everyday life, there were issues. And with some of the advances in mathematics of the 14th century, and some of the advances in optics in the 14th century, so coming out of the medieval Renaissance, or the Renaissance of the 12th century, and then the new recovery of Aristotle, further developments, Copernicus said, you know what? I can save the phenomena better with a different theory. Now, the term to save the phenomena, what does that mean? It means we observe. And what do we observe? And then how do we account for what we observe? We come up with a theory to explain what it is we observe. That was the basis of medieval science, medieval natural philosophy, Greek natural philosophy. And, as I will argue, was the basis for early modern science. In some ways still is. We observe and try to figure out, why does this happen? How do we describe it? How do we explain it? Can we predict what will happen next if we do it again? Now, there's more to the scientific method today, and as it was developing in the course of the late 16th on into the 17th and 18th centuries, than simply that. But the fundamental principle That's what medieval natural philosophers were doing. They were observing and saying, how do we account for this? How do we save or preserve the phenomena that we see? And the Ptolemaic system worked extremely well for that. It just started getting a little bit off. It wasn't quite good enough in focus. And Copernicus came along. I said, you know what? I can do a better job if I posit as a theory, to account for what is observed. I'm not saying this is the way it really is, but to account for what is observed, if I put the sun at the center of the universe and have the Earth orbit the sun. Now, going back to the Ptolemaic model that I put on the slide a few slides back, all he did was switch the sun and the Earth. So the Earth would take the sun's place in the third position, on the third sphere, and the sun would be at the center. A heliocentric universe as opposed to a geocentric universe. The Ptolemaic world system was a geocentric universe. Now, Copernicus wasn't the first to propose this. They have up there Aristarchus of Samos. Aristarchus, as you see the date, and that is the correct date, approximately 235 BCE, means before Christianity and everything else. 200 years, 235 years before it all, and all. Posited a heliocentric universe. Now, he has been called the Copernicus of antiquity. And he met with universal rejection by the Greek natural philosophers. Why? Because they said, Aristarchus, yeah, fine, that's cute. It works, sort of. But it's insanity. Because if you put the sun at the center, they're still working with this Ptolemaic idea of concentric spheres. To have it all work out, to save the phenomena, if you with the sun at the center. Now, I don't understand this because my math isn't all that much. They did. They said, that would mean that outermost sphere of fixed stars would have to be so far away. It's inconceivable. My God, we can see the stars. And Aristarchus was rejected. Copernicus said, let's work this out mathematically, because at least it works better to account for what we see. And by 1533, his positions were known and were being discussed. I have up there his treatise De Revolutionibus Orbius Celestium, on the revolution of the heavenly orbs, or heavenly spheres. It wasn't published until after his death, until 1543, but it was being discussed there for a decade already while he's still alive. It dedicated it to the Pope. Pope thought it was great. He did so because he thought this can help with the calendar. And at the time, the Pope is trying to revise the calendar to make it more in sync, so we don't end up having, Easter in December and Christmas in, when it's hot outside. So let's somehow bring it more into sync. And Copernicus said, here's a way, if we use this, it can work. The Pope thought, this is great. And actually did use it for calendrical reforms. A Gregorian calendar, much better calendar than the Julian calendar of Julius Caesar. And it kind of worked better. Now, there were some natural philosophers who had the same reaction to Copernicus as the Greeks had had to Aristarchus, saying, Copernicus, you're crazy. This is not right. We can see the stars, etc. Others were saying, well, maybe he's actually right, and maybe the stars are that far away. Keep in mind what's going on in 1543. The New World had been discovered. The Reformation was happening. People were breaking away from the Roman Pope and the institutional church. This whole new world was discovered, made by the Europeans, in the Europeans' minds. Maybe things are very different from what we always assumed. The older paradigm was being challenged. There's always resistance. There's always resistance to change, to radical change, to significant change. And it only comes to a certain point where then there's a kind of a flip, where a new paradigm is beginning to emerge from the critiques of the old paradigm that is seen as not working anymore. And Copernicus really signals, along with Columbus and the discovery of the New World and all the other discoverers and the whole period of colonialization and everything else we've been talking about, as contributing to this beginning of this transition period from one paradigm to another. And in the 16th century and the 17th century, we're not really there yet. But Copernicus was not condemned by the church because he questioned the Bible. That is complete bunk. Now, theologian Martin Luther rejected Copernicus, whereas Philip Melanchthon, his right-hand man, thought he had a lot of interest, and actually one of the big proponents of Copernicanism and of Copernicus' views was a man by the name of George Rheticus, who was a student of Melanchthon at Wittenberg. And Melanchthon got Rheticus to read Copernicus and really think about it. And so there's even there at Wittenberg, we have Melanchthon positive towards Copernicus and getting Rheticus being a hardcore proponent of Copernicus. We have Luther saying, no way in hell. It contradicts the scripture. When God stopped the sun for Joshua, the Battle of Jericho, he didn't say he stopped the earth. He said he stops the sun. Well, I said, yeah, wait a minute, that's one perspective. Anyway, the whole point being to this is that what is so often portrayed as this opposition to Copernicanism was an opposition by the best scientists of the day. No, footnote, Luther was not one of the best scientists of the day, but it was the best scientists of the day opposed Copernicus. And when some of the other scientists thought maybe we should listen to him and go further, and Copernicanism wasn't condemned until later with Galileo, and I'll be getting there in a minute. But that is what was going on even after the publication in 1543. But there was controversy, there was uncertainty, because all of a sudden this new theory that seemed to work. And then we had people like Brahe and Kepler coming along and refining Copernicus even more. So you know what? It's not really circular motion, it's elliptical motion. And we get other further fine-tuning of Copernicus's theories that makes it then, oh my gosh, what's going on here? And if it's elliptical, then how can the Ptolemaic universe remain as our model? It's like it no longer can. Whereas other scholars saying, no, it is. And we have this tension. And it's in this tension, in the later 16th on into the earlier 17th centuries, that the advocates for Copernicus, and then Brahe and Kepler, started politically trying to win the cause and get Copernicanism accepted as the reality of the universe, and so started denigrating those people who were not accepting Copernicus after 50 years or more. And they started saying they're so backwards they believe the earth is flat. That's where the whole theory of the flat earth started, was in the early 17th century by scholars who were denigrating the holdouts to the old paradigm. What was Einstein's response to quantum mechanics? God does not play dice. Even Einstein had his limits to say we can't go that far. I'm not willing to go that far. That's what a lot of scholars, a lot of natural philosophers were saying with Copernicus. I can't go that far. Whereas other people did. And what really changed things was not just the theoretical model, of Copernicus, and then Kepler and Brahe with the ellipses and things, which would completely blow away the Ptolemaic system. But it was with Galileo and what Galileo did. Galileo, up there, 1654 to 1642, was a devout Christian. He was very good friends with the Pope. And he was a scholar. And he pursued natural philosophy based on observation and experimentation. And he did something that no one else had done. Before the publication of his first controversial treatise, The Starry Messenger of 1610, Galileo, he's famous for the inclined plane experiments, also started doing real experiments. Take a big boulder and a small pebble, drop them from a tower, which is going to hit the ground first. They hit at the same time. That is what Galileo proved, which is, counterintuitive. You have, a 500-pound rock and you have a, half a pound pebble. You drop them, they both hit the ground at the same time. Even though the gravitas of the boulder and the pebble are completely different. It's all with resistance and air resistance, all these things that we know, just assume, but at the time didn't make sense. It's like, wow, rolling it down in inclined plane, same thing. So, whole point with his physical experimentation, not just mental, not just intellectual experiments, but actual physical experimentation. I mentioned eyeglasses, medieval development. Also, they had magnifying lenses, eyeglasses, magnifying so we can read more. And they used it for navigation, to see, spy glasses. It was a big help in the period of exploration. It was a medieval development, technological development of what to do with glass. I have no idea how it's done, but what to do with the lens grinding, maker of lenses to make something that will magnify what you see when you look through it. Galileo said, instead of using a spyglass to look out on the horizon, what if I make trying to get a really powerful magnification lens, and my spyglass look up? And that's what Galileo did. And it blew his mind. Because what he saw was craters on the moon. Craters on the moon. Those four elements. I left one out. Because those four elements in the medieval natural philosophical world, earth, water, air, fire, were for what was called the sublunar realm, the realm from the moon to the earth and on the earth. Anything from the moon above was all made out of a single element named ether. Ether had the natural motion of perfect circular motion. That's why I said the Tycho Brahes and Kepler's elongation and elliptical orbits freaked people out too. But it still was just a theory at the time. But the planets were also made of ether, being spherical. So when you saw craters on the moon, all of a sudden it's like, it can't be made out of ether. Because ether is perfectly spherical and moves perfectly spherically. He saw the rings around Saturn. He said, what the hell is that? He saw that what is observable is not what we thought. He saw more. And he writes up the Starry Messenger about it in 1610. And because he had the proof and the evidence, he's not just saying, I can account for what we observe better. That was Copernicus, and that's why the Pope said, okay. He said, no, you know what? Copernicus was absolutely right. Not just theoretically, but physically. The physical reality is correct. And all that we thought, the Ptolemaic system, and all that we thought we knew about the cosmos is wrong, and I can prove it because I've seen it. We need a new model. Now that started getting all kinds of problems. And from 1616 to 1613, the whole approach to Copernicanism started to be re-examined. And it's like, maybe we should condemn Copernicus. Galileo was condemned. It was brought before the Inquisition, was cleared. The Pope was like, what do we do? Blah, 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 blah. And then in 1632, he reads the Dialogue Concerning Two Chief World Systems, and that gets him condemned finally. He's condemned as a heretic, at least in terms of his natural philosophical writings, put under house arrest. He's not executed. He's just put under house arrest. And Galileo was condemned, and then Copernicus was condemned along with Galileo. And this becomes the beginning of this split between the institutional church and natural philosophers. Galileo was a very devout Catholic. So was Copernicus. Both Catholics and Protestants rejected Copernicus. More Protestants started embracing Galileo for no other reason because his views were challenging the institutional church. But Galileo was a devout Catholic. He also came up with a whole new cosmological view, since the Ptolemaic system wasn't right, and the ether and four element system wasn't right, namely one of atomism, which is kind of going back even behind the elements. Everything is comprised of atoms. It's actually a Greek model too. Greek natural philosophers who were atomists. Lucretius was an atomist. So he brings that back, and that has been argued, I think fairly persuasively, that was really what was behind Galileo's condemnation, was his physics, not his cosmology or astronomy. Because in Galileo's physics of atomism, that rendered impossible the doctrine of transubstantiation, which had been the doctrine of the Eucharist since the 1215, the Fourth Lateran Council. And so when you start messing with not just how the universe works, and how to harmonize that with statements made in Scripture, but when you condemn what had been proclaimed as official Christian doctrine in terms of the Eucharist, the central mystery of the Christian faith, that's more problematic. Now, the Protestants didn't have any problems with transubstantiation. They didn't accept it anyway. The Catholics did, but we need to make this distinction between faith and belief, the institutional structure of the Catholic Church and the Roman Catholic Church, especially in light of the Reformation. This is the Counter-Reformation Church, opposing Protestantism, not wanting another schism. How do we deal with this? Because we've already lost so much. How do we hold on to what we had? Can't we just go back to the old paradigm? We need to preserve that, being afraid of the new. That's the institutional church, which is not the same as faith and belief, which is not the same as Christianity and belief, or religion and science, or anything else. And then we have the natural world, and all along from the Middle Ages, throughout this period too, one of the fundamental processes was that God has revealed God's self, which is my term because they would say himself. They would have used the male pronoun. But God has revealed God's self in two ways. Well, three ways actually. But one through Scripture, two through Jesus, the incarnation of Jesus, and then three through the book of nature, as it was called. The book of nature, the book of Scripture, the Word incarnate, and the book of nature that God had created. And the book of nature, you can't have conflicting revelation. And so if the book of nature says one thing, we have to understand the other two in light of the book of nature, which we can understand by reason because it's all natural causation. That's where this is all going. It's not a conflict between faith and reason or religion and science at all. It's a conflict between new natural discoveries of the natural world with the institutional Catholic Church, and sometimes, to some extent, with the institutionalized Protestant churches. And two, the question starts becoming, it's one thing for scholars to debate some of the things, but what do we teach the people who can't really understand it all? We have to be careful. I'll come back to that in later lectures because that's going to be a big issue when we get into the 20th century. 21st century, I'm not even sure if I hope to come back to that in some ways. If I don't, maybe remind me. But some of the problems with the institution, the institutionalized Roman Catholicism. It took a long time for the Catholic Church to admit they were wrong about Galileo. Um, they held on to it for as long as they possibly could. It was somewhat recent. I forget exactly when, but 20th century certainly before they could. Yeah, Galileo was right. A mess. But that was Galileo. And what it showed was that the old paradigm was no longer possible to maintain. A new paradigm had to be found, established. We need to somehow put everything together where it all makes sense into one whole. Because what had been there, we now know is not there. It's not right. It doesn't work anymore. It doesn't accord with what we observe. Along comes Isaac Newton. Now, Isaac Newton, we all know, he published his Philosophiae Naturalis Principia Mathematica in 1687. He wrote it in Latin. It is translated as the Mathematical Principles of Natural Philosophy. I think Newton was still a natural philosopher. He didn't refer to himself as a scientist. He's talking about natural philosophy. It's usually abbreviated simply as his Principia. And Newton, and I know I'm running out of time here, so I'm going to try to abbreviate this somewhat because I think you probably know about Newton, but in his Principia, we find the mathematical description of the three laws, universal laws of motion, saying, there are laws that govern all motion. An object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by a contrary force, an opposite force. Rather than natural motion and violent motion, Newton sees it as competing forces. Impetus is what he said. Impetus. An object at rest has the impetus to remain at rest, and an object in motion has the impetus to remain in motion. That, too, was a medieval term that was used to talk about the motion of things and how do we describe it. Newton developed calculus. The Oxford calculators are already said in the 14th century, early 14th century, had come very close. But Newton does too. Now, it's often said that Newton and Leibniz in Germany more or less simultaneously discovered calculus and developed calculus independently, but yet most scholars will say that, well, yeah, but Newton, we can see it was actually earlier than Leibniz, but they knew each other. There was talking back and forth, but anyway. But the point was that he developed the mathematical constructs to describe things as they had never been described before. And so he starts describing things that had been medieval terms. Gravitas. Why does the book fall? Not because it has a natural motion down towards the center, but because there are attractive forces based on mass, and I don't know what it all is. I can't figure it out mathematically, believe me. But two bodies have attractive force on each other, and one of larger mass will exert more force on attracting a smaller mass object. That's why we don't just go floating off, because the Earth is so huge that the gravitational force that the Earth exerts on us keeps us here, and does so on whatever part of the spherical Earth we're on. Gravity is just a mathematical explication with the use of forces and the laws of nature to describe what in the Middle Ages have been described by natural motion and a rational description of what is observed. And Newton says we can be more precise. We can be more precise and describe it all mathematically. It's really then with Newton that mathematics comes to the fore. I already mentioned Aristarchus. Back in 235 BCE, he was rejected because to work it all out mathematically, it'd be so far away, not possible. Copernicus was working out mathematically. The calendrical reforms are based on astronomical mathematical formulations, but all of a sudden, then mathematics could describe all of observable nature and explain it and predict it. Gravity, the laws of motion. We can't explain it. And the whole entire universe functions according to laws. It's a mechanical universe. It's a mechanical universe that can be charted, diagrammed, explained mathematically. God is not needed. And often we see Newton as being not only part of the scientific revolution, but also part of the Enlightenment. And we'll see in next lecture with the Enlightenment that we have emerging what has been called deists, the deism and deists. And the deists were people who claimed and argued that, yes, there's God. Deism is Deus, Latin for God. There's God. God created everything. And then sat back, said, you know what? Good luck. You're all on your own. Everything works according to natural laws. The image of God as a clockmaker was a medieval image, but it became very much an image in the fore in the Enlightenment, with God as the clockmaker, who simply all God did was set the pendulum in motion. Everything else works by natural laws, by natural causation. Principles that emerged in the Middle Ages as their attempt to describe what they saw and predict what they would see based on natural causation. With Newton and the development of mathematics, becomes all of a sudden this is the new reality. This is new. And we've seen more. Technology, like the telescope, leads to seeing more, which blows our minds, that we can all then describe mathematically and how the whole universe works as we keep trying to see more and more and more. That's where all of this was going. To the point where I have up there the Enlightenment figure, Alexander Pope. There's his dates up there. He's a British poet and Enlightenment thinker, and he wrote, "Nature and nature's laws lay hidden night. God said, 'Let Newton be,' and all was light." And yet Newton was a very religious person. He had some really pretty kind of weird views. He was sort of close to being an anti-Trinitarian. He was a millenarian, believing in the second coming of Christ to end the world and all. So he was a devout Christian. And if you said, wait a minute, you're a scientist, how can you hold religious beliefs? You say, what are you talking about? There's no conflict. You're crazy. That's what I want to get across, that this conflict of faith and reason, of religion and science, is a modern development and conflict. Yes, the institutional church kind of gets into it, which makes things much more difficult, beginning with Galileo. And so there's this kind of official position. But in terms of the abstract faith and religion, no. Begin to be an opposition of the institutional Catholic Church with natural philosophy. You want to say that's science and religion? Okay. But that doesn't mean that people are religious or religious people have a conflict with it. It means that the institution has a conflict with it. Newton didn't have a conflict with it. I mean, he had a conflict with the institutional Catholic Church because he wasn't Catholic. He was an Anglican. And he was, professor of mathematics at Cambridge, or pointed to it, and he kind of refused to be ordained because it was a law or a rule that to be named to a professorship at Cambridge, you had to be an ordained clergyman in the Church of England. He got out of that. The king granted him permission not to be ordained and still to be appointed as professor of mathematics. But that wasn't because he didn't believe thoroughly. He just believed his own stuff. He didn't really believe what the Church of England was going to say. So he says, I'm not going to become an ordained pastor of the Church of England because I think they're wrong because I have my own theological ideas. And which are still under studied for Newton. But that's how it all comes about. And we need to see these developments historically rather than reading back our own problems and issues and conflicts. And we will see when we get there, this split just even became worse when we get to Darwin. This between science and religion, and almost it becomes more general. science and religion. But then, does that mean the same thing as faith and reason? Well, we'll get there when we get there. But for now, there's not that opposition. There's an institutional opposition to the new natural philosophy. There are the holdovers from the old paradigm that weren't convinced. But with Newton, and as Newton catches on, the new paradigm has been established. Kind of from Copernicus, from De Revolutionibus until Newton's Principia, is a period of transition. But with Newton, we have the emergence of this new modern paradigm that would stay until the early 20th century with the new physics, which we'll get there when we get there, which is one of the first aspects of the indications that we're no longer in the modern paradigm, but are moving into a postmodern paradigm for which we still don't have a better term yet. But we'll get there when we get there. Now that is kind of what I have to say today, and I'm just at the just over my time limit for a little bit, but that's kind of the last slide here, faith and reason. I basically have already addressed that, I think, throughout, but also with my last expose on Newton and stuff. So I will leave it at that. But, and also read the textbook on these developments. But what I wanted to emphasize to you is that these periods of historical change, from the medieval world to the modern world, the early modern, were complex. And it may be a banal statement, like they were complex. And it's not so much in opposition. History is not all of a sudden somebody drops out from heaven, something new, boom, we reject what's old, bring in the new. That's not the way it ever worked. It's a development and a process and a learning and a growth and a period of discovery. And then sometimes things are discovered that are so earth shattering, that so blow apart what we previously thought, that we can only see it as revolutionary. That's why the scientific revolution legitimately can be called a scientific revolution, because the discoveries were revolutionary and forced a completely new approach to reality and the world and the cosmos in which they found themselves and in which we still find ourselves today, and the emergence of a new paradigm, one that will continue throughout modern Europe. And as I said, I think we are struggling, in my view interpretation, we are struggling with the increasing disintegration of the modern paradigm, not knowing who the next Newton will be to put it all together in all facets: social, cultural, scientific, intellectual, theological, religious, political. You have it, where everything makes sense. We're in a world of chaos, but we'll get to that world when we get there. And this is for everything else that we've been talking about leading up to your first midterm in terms of the emergence of early modern Europe. Thank you so much. Bye-bye.